So Assalamu alaikum everybody, Bismillahirrahmanirrahim. We'll start with Qadrature Amplitude Modulation. So over here, when you say Qadrature Amplitude, so you are changing two things. First is you're changing the phase of the carrier, and then you're changing the amplitude of the carrier. Alright, we are changing the phase of the carrier so that we can transmit more signals. In this case, the phase will be shifted by 90 degrees. Okay, this is why it's called quadrature. So that means you can transmit two signals together, and the amplitude of the carrier of both the carriers will change based on the message signal. Okay, let's understand that. Let's see the block diagram. So I have message 1 and I have message 2. Two different messages. The first message, because it's amplitude modulation, so multiply with carrier. And now the same carrier is phase shifted by 90 degrees, and you will again multiply with the second carrier. And both of them are then added. And this is your QAM signal. This is cosine omega ct, and when you do cosine omega ct minus pi by 2, you will get sine omega ct. Okay, so message 1 multiplied with cosine, message 2 multiplied with sine. So QAM signal, if you look at mathematically, it's m1 cosine omega ct plus m2 sine omega ct. Right? Now you will have to find the Fourier of that, Fourier's transform of that, and so this is how it looks like in time domain. Please see how it's going to look like in frequency domain. Okay, so that should be in your report. All right. Okay, let's go to the demodulator now. In the demodulator side, the whole QAM signal will be again multiplied with the same carrier, cosine omega ct, which is again phase shifted to give you the second carrier, right? And then this passed through a low pass filter to give you a scaled M1, because M1 must multiply with cosine. So in the demodulator side, if the same omega ct is multiplied with the QAM signal and then passed through a low pass filter, you get scaled version of M1. Scaled means it can be half, 1 by 4th, and so on. We can see that, right, mathematically. Similarly, when this goes through a low pass filter, you get scaled M2. Okay? Now, at any point of time, for example here, if I need to know what is my signal, it's QAM signal multiplied by cosine omega ct. So that's, again, we know what the QAM is. So QAM is m1 cosine omega ct plus m2 sine omega ct, the whole multiplied with cosine omega ct. Alright, obviously you will have something like this, m1 cosine square omega ct plus m2 sine omega ct cosine omega ct, right? Using the trigonometric functions, you will see that at the end we will have some high frequency components and then low frequency components, which when passed through a low pass filter will get rid of these high frequency components, and you will be left with the low frequency signal, which is M1. Okay? Alright? Same thing happens over here. When you multiply with sine omega ct, if you do the math again and then pass it through a low pass filter, again the high frequency component goes away and you're left with only M2. So as you can see over here, we are transmitting two signals, and at the end we are getting back the same signal back. We are getting the signal, the desired signal, by just multiplying with the respective carrier frequency. One thing you have to be, you have to take care is, we should always avoid, suppose if there is any sort of phase shift, if there is any sort of phase shift here or here, okay, over here there's a phase shift, that means it's not the same carrier that is multiplied, it's a carrier with a phase shift, then you will not have KM1 alone, you will have a distorted signal. So you will have also M2 here, okay? Obviously you have to do the math, alright? Or do the whole formulation thing. This should be there in the report. Same thing, if there's a phase shift over here, then you will have KM1, M2. As you can see, there's interference now. So the best way to fix that is, when you're multiplying it, have a phase shifter. This is called as a phase shifter, and this phase shifter will get rid of the extra phase that is there, so it will remove that phase, and at the end you will be left with cosine omega ct, and then you will not have this extra interference. Similarly, over here again, before it goes, so let me write it over here, it's sine omega ct plus phi. So you will have again a phase shifter here, which will make sure that what you're multiplying is sine omega ct, and at the end there will be no interference, right? So that can be easily seen when you do it in the same way. Okay, we have seen how to do that in our previous labs, right? So that will be something that should be there in the report. Okay, it's also there in the videos, you can refer to them. Alright, so this is what our QAM modulation and demodulation looks like. Now we'll go and look at it physically. Okay guys, so now we have the whole module set. Let's go through them step by step. So this is my speech module, and I have two signals. Let's hear to them. That's my first message, and the blue is my second message. Alright, so now what I'm going to do is, the first message is multiply. This is a quadrature utility, so it has two multiplier, multiplier 1, and there's multiplier 2 at the bottom. This is the quadrature utility. As you can see, it has two multipliers, right? So this will be the signal and the carrier. This will be the second signal and the phase, like 90-degree phase shifted carrier. And the output of the multiplier goes into the adder, output of this goes to the adder, and the final output is my QAM signal. So that's what I did over here. So that's my message 1 multiplied with sine, okay, high frequency sine signal, and then message second signal multiplied with 90-degree phase shifted cosine, and then this is the multiplier output 1, and this is multiplier output 2 that goes to the adder, and this is my adder output, which is my QAM signal. Alright, now I'm taking the QAM signal as an input to, now this is my modulated signal. Now this is my demodulator. So in the demodulator side, the QAM signal is going to a multiplier, and it is multiplied with, because I want to get message 1, which is multiplied with sine, so my QAM signal is multiplied with a phase shifted sine signal, and we'll see the effect of the phase. And then that signal goes through a low pass filter, and then, so this is my message 1. Same thing happens for message 2. The QAM signal is multiplied with phase shifted cosine signal, because in the modulator side I'm multiplying with cosine, and then that is passed through a low pass filter. So let's listen to it now. So that's my first message, right? No interference, right? But what if there was some phase difference between the carrier that was used here? What if there was a phase difference between the carrier that was used here and the carrier that is used here? Let's see the effect of it. You see, there's an interference. There's an interference. So if you want to fix it, I have to do a phase shifter. Okay? So you see, there's an interference. So if the phase, if the carrier that is used here and the carrier that is used here have some phase difference, is going to cause interference. As you can see, there's an overlapping between the messages, and the best way to fix that is have a phase shifter that will clear it out. Same thing, if you go and listen to the second message, which is here.
Second message. Bismillah, second message. Bismillah, second message.
Now, as you can see, the second message is clear, but there is still interference from the first message, and in order to fix that, I have to be very careful with my phase here, right? So this is an experiment purpose. So, but the whole objective is that you are sending two messages, you are getting two messages back. There might be some difference, and that is because of the phase difference between the carrier used here and the carrier that are used in the demodulator side. So the more costly equipment you use that can even fix small amount of phase, the better or the less interference you will have in the demodulator side. Okay, thank you. So in the previous video you have seen how the modulator was made and the demodulator was made, and we had seen how we can look at it in time domain, and obviously do the Fourier transform of it to look at it in frequency domain. So I'm just going to give you some hints on how it is going to look like, and you will be able to relate it to what you have seen earlier. Alright? Obviously this is clear why it's called quadrature amplitude, because the phase of the carrier changes. As you can see, there was a cosine and it is phase shifted to accommodate the second signal, and the amplitude of the carrier is changed based on the message, which is evident from the multiplier, right? We have two multipliers here. So if I look at this signal and I say M1 is equal to 2 kilohertz and M2 is equal to 10 kilohertz, and the carrier omega c is actually 2 times of pi times of 100 kilohertz. So the signal that is over here is going to look like, I'm sure you know by now, is going to be centered at 100 kilohertz. Okay, everything is 100 kilohertz, and I'm looking at the magnitude of m1 times cosine omega ct, right? So it's going to be 100 plus 2, 102, and that's going to be 198, and it's going to be half. And the same thing happens over here. Yeah, same thing will happen here. So again, this is 10 kilohertz, so it's going to be 100, so it's going to be 110 and 90. And this is again fast Fourier transform, magnitude of the Fourier transform of m2 multiplied with sine omega ct. Right? So obviously the QAM signal is going to look like 100, and then 1 here, 102, 110, 98 and 90. So there will be 1 at 90, 98, 100, 102. Right? similarly, you can go ahead and look at it afterwards, right? Remember, this is what you have seen in AM modulation. Over here, this is also in AM modulation. And over here, it's actually summation of two AM signals. Alright? Thank you.